Hi everyone, thanks for joining our webinar today. My name is Charles Chung, and today we'll be talking about how to achieve system cost reduction and performance optimization using the RocketMEMS semi-custom pressure sensor platform. You may have found us on some of our articles that have recently been published. We were recently on the front page of Sensors Online magazine with an article of the same name. That's my colleague Paul Werbineth and me. Paul is on the left and I'm on the right, and we had published an article with the same title. We also published an article titled Choosing MEMS Pressure Sensors for Medical Device Applications in Medical Design Briefs. And finally, we also published an article titled Tailored MEMS Sensors for Customers Seeking Business Opportunities in a Long-Tail Marketplace in CMM magazine. If you'd like a link to these articles, or if you'd like more information, please visit our website at www.amFitzgerald.com/publications. So let me give you an overview of our talk today. First, we'll talk about what semi-custom pressure sensors are, and then we'll discuss and give a few examples on how you can use the customization of these devices to benefit your system, in particular how to increase system performance, how to decrease system cost, and how to improve system reliability. We'll also talk about how to scale volume, how these devices can scale in volume, production volume, to meet your market and application. And finally, how to move forward and what the next steps will be. We'll end with some questions and answers. The whole webinar should take about 20-25 minutes with questions, 5 to 10 minutes of questions and answers at the end. If you'd like to ask a question, let me point out that there is a question, there's a chat box in which you can ask questions to me in your GoToWebinar interface. So what are semi-custom pressure sensors? Well, semi-custom pressure sensors are devices based on existing reference designs that were developed for an established production-proven fabrication process. Semi-custom pressure sensors have a degree of customization with less risk and cost compared to a fully custom device. So what does this mean? Well, typically for a MEMS device, you have two choices, where you can either purchase something off the shelf, or you can create your own custom MEMS device. With your off-the-shelf device, the sensor specification is fixed. In other words, the pressure range, the pressure sensitivity, the device impedance, parameters such as this are fixed and can't be changed. Likewise, the fabrication process, or the method to make these sensors, is also fixed. The benefit of this approach is that there's no development time and there's no development cost. At the other end of the spectrum, you have custom MEMS, and with custom MEMS, the sensor specification can be whatever you want. You can set the range to whatever you want, the sensitivity to whatever you want, the impedance, things like this. And the fabrication process is likewise custom, typically optimized to meet your sensor specification. The cost of this, though, is that the development time is typically on the order of years, and the development cost is typically on the order of millions of dollars for the entire project. In between, we have semi-custom MEMS, such as AMFitzgerald RocketMEMS. With semi-custom devices, the sensor specification can be customized. You can adjust the pressure range, and you can adjust this pressure sensitivity. But the fabrication process is fixed. And this compromise allows a development time on the order of months instead of years, and a development cost in the order of hundreds of thousands of dollars instead of millions of dollars. And what we found is that many pressure sensor application needs may be met with the RocketMEMS semi-custom approach. In fact, most pressure sensor application needs may be met with RocketMEMS with a semi-custom approach. So how can one customize the sensor specification but fix the fabrication process? Well, let's talk about how semi-custom works. Semi-custom devices start with an established, stable, in production process. So this is the cross-section of the device, and you can think of that, this cross-section or vertical stack as being defined by the fabrication process. And it's the development of the fabrication process, the method to make this device, that is the expensive, time-consuming, and risky part of semiconductor chip development. This is a view of a pressure sensor from the top. This is an actual photograph of one of our RocketMEMS pressure sensors. You can see in this photo the deflection of the membrane under 1 atmosphere. That would correlate to this in the side view to that thin line deflecting into the white cavity underneath. The features from the top, they're they're dimensioned in the X and Y direction or in the lateral directions. They're defined by the masks. And lateral features or mask-defined features are easier and less risky to change. So you can change things like the membrane width and size, the location of these 4 piezoresistors at the north, south, east, and west edges of the membrane, things like this. So what can you change by changing just the mass and fixing the process? Well, there's a lot actually. You can change the die length, width, and thickness. You can change the pad size, number, and material. We can change the membrane length and width and thickness, and you can also adjust the burst pressure. Under electrical parameters, we can change the offset voltage of the bridge, of the device, the power draw, the bridge resistance. We can also change the circuit architecture to be either a full bridge or a full Wheatstone bridge or a half Wheatstone bridge. And finally, you can change important parameters like the pressure range and the pressure sensitivity of this device. Let me give you a sense of how much flexibility you have in some of these parameters. We can't go through all of them, but we have three sectors here: medical, consumer electronics, and industrial or aerospace. For chip length or width, the chips can range from 0.3 to 2 millimeters, and they can be larger than this and they can be smaller than this. But we're just for the purpose of this slide, we have some example applications for some example specifications for some example applications. The thickness can range from 0.3 to 1 millimeter. The bridge resistance can go from 1 to 10 kilo ohm. Under medical pressure ranges, these can range from half an atmosphere to 1.5 atmospheres. Now this is basically all the pressures that you're going to find in the human body, and these allow one to use these pressure sensors to monitor blood pressure or to monitor flow. Under consumer electronics, pressure ranges may be from 0.2 to 2 atmospheres, which enables the most popular consumer electronics applications like altimeters or barometers. And finally, in the industrial aerospace sectors, the pressure range can go from 0.2 to 10 atmospheres, which allows fuel gauges and hydraulic systems and many other applications. So there's a lot of customizability within the semi-custom space. How can you use this to increase system performance, reduce system cost, and improve system reliability? Well, we'll go through a few examples now. Let's first talk about how to improve system performance. This is a sensor output-input graph. Along the x-axis, we have the sensor input, which is a pressure for a pressure sensor. In this case, it's measured in atmospheres. Along the y-axis, we have the sensor output, which is voltage, typically measured in millivolts. And the blue line here is the typical sensor output versus input-output line for your typical off-the-shelf pressure sensor for barometric applications. Now, barometric pressure is the same as atmospheric pressure, and it's useful to measure this. It's useful, for example, for monitoring the weather. And this sensor is kind of very typical of an off-the-shelf pressure sensor used for barometers. For example, at 0 atmospheres, the output is 0 millivolts. And at the high end, well, you expect the atmosphere to be around you expect the barometric pressure to be around 1 atmosphere. And there's a little bit of buffer above, say a 20% buffer, to make sure you are able to capture all barometric pressure. So the maximum range may be something like 1.2 atmospheres. Now, this red box represents the actual range of atmospheric pressures. I mean, for example, this right-hand edge is, for example, the highest recorded barometric pressure ever observed in history. That occurred in Mongolia in 2001, and it measured at 1.085 atmospheres. Likewise, this left side edge is the lowest recorded barometric pressure in history. That is occurred in 1979 in the Pacific Ocean during Super Typhoon Tip and measured 0.870 atmospheres. So actually, the entire barometric application pressure range is 0.87 to 1.085 atmospheres, which means that this entire output of the sensor is never used. And one way to view this is that the span of the application and the span of the off-the-shelf sensor are not well matched. The off-the-shelf sensor will work for this application, but is by no means well optimized. What if instead we had a sensor represented by this red line that passed through the diagonals of the box, of the application space? And in order to have a device like this, you'd have to have a custom slope, which means, which is also the same as device sensitivity. And you'd also have to have a custom intercept so that you could position the line so it passed through the diagonals of that box. And if you're able to do this, the sensor now fills the application span. So let's blow up the application space in the next slide. And again, we have the blue and red lines for the off-the-shelf pressure sensor and for the matched pressure sensor. And the off-the-shelf sensor will have, at the low end, at the lowest atmospheric pressure, will have an output of 61 millivolts, and at the high end will have an output of 76 millivolts, which results in an overall output or span of 15 millivolts. But in contrast, the matched pressure sensor will have an output of 0 millivolts at the lowest pressure and 76 millivolts at the highest pressure. We'll make it the same as the other sensor to make it easy to compare, which results in a span of 76 millivolts. And the result is now the application, in the matched sensor, the application span and the sensor span are matched, and the result is that the sensitivity of the device is increased by a factor of 5 to 5x. So nothing's changed. The rest of your system can remain the same. All you've done is replace your pressure sensor, your off-the-shelf pressure sensor with a matched pressure sensor, and your system now performs 5 times better. So let me give that was an example of how to increase performance with a semi-custom device. Here is a way to increase system cost or decrease system cost and increase reliability with a semi-custom platform. Let's talk about something as innocuous and overlooked as bond pads. Bond pads for a pressure sensor are typically, and for most chips, are typically optimized or positioned optimally for the chip. So for a pressure sensor, the bond pads are typically located at the north, south, east, and west locations, and the reason why is because typically there's a Wheatstone bridge, and the Wheatstone bridge input outputs are at north, south, east, and west. So. Now, the output of the pressure sensor is typically read by an ASIC, and the bond pads for the ASIC are typically laid on one edge, and the reason why is again, the internal data flow is linear. The data goes from an input stage to an amplifier to an analog to digital converter. And so all the bond pads for the input stage are located on one edge. And in order to map the output of the pressure sensor to the input of the readout chip, you typically need a third component, which is the PC board, which will have pads arranged something like this. And then finally, you can wire bond these up and get the two chips communicating with each other properly. So this is the situation for when the bond pads are positioned optimally for each individual chip. Now, what if instead you had a system and you've already picked out the ideal readout chip for your system, and now you're looking at a semi-custom device? Well, you can set the bond pads so that they match your readout chip, and now you just have wire bond directly across. And you can do this with a semi-custom chip because you're able to specify things like bond pad location within the information context of what the other chips in your system may be. And by doing this, we've now removed one component, the PC board, removed 4 wire bonds, and we've now reduced the cost. We've increased the reliability because wire bonds are typically a typical point of failure in electronic systems, and we've decreased the overall system size. So this is an example of how a semi-custom approach can reduce system cost and improve reliability. Let me also talk about scaling production die volumes. This is a picture of an actual RocketMEMS wafer. You can see that there are multiple designs on here, and that's possible when you are changing designs just by the mask. And what this allows us to do is put multiple designs on run and also scale die volumes with your needs. So what we would do is simply adjust the proportion of the area of the wafer to your device. So we can have as few as 500 devices for rapid prototyping needs. When you're in low volume production, we can have scale up the number of devices to 1,000 devices per year or tens of thousands of devices per year. And finally, when you're ready for high volume production and ready for millions of devices per year, you can order the entire batch to be dedicated to your design. A batch is typically 25 wafers. So the way this program works is that if you're interested in a semi-custom device, the customer or you would provide a specification to us, AMFitzgerald. We would translate that specification into a design. We then work with Silex Microsystems to fabricate your chips. And finally, you would receive your bare pressure sensor die in 4 to 5 months. All the die are 100% tested. They're all known good die. And as far as we know, this is a feature unique to the RocketMEMS program. You'll probably need other parts of your system, such as the readout electronics, perhaps an ASIC, perhaps packaging for your device. These are things that we don't offer right now, but we can offer support and recommendations for them. If you'd like to evaluate our pressure sensors, we have an evaluation kit. The evaluation kit includes one of our RocketMEMS pressure sensors, a readout chip, a board, and a cable to connect up to your PC, and software and a manual. This evaluation kit allows you to monitor the pressure, temperature, as well as the pressure. The output of both these quantities is in raw digital output. And the reason why we did that is because we wanted to provide to you as transparent and as raw look at this pressure sensor itself. So there's no compensation algorithm, there's no calibration algorithm running. And so you can now put this board into a pressure chamber and sweep the pressure up and down, and the software will also allow you to log pressures as you go up and down in pressure. Let me say a few words about our manufacturing partner in the RocketMEMS program, Silex Microsystems. As you can see on the left and right columns, Silex has made a lot of different MEMS devices. In the photos in the middle, you can see in the upper left-hand corner that they have a lot of experience also with making pressure sensors. Silex is a dedicated MEMS foundry. They make no other kinds of devices, and they have now more than 13 years of MEMS production experience. And they've worked with many of the world's top MEMS companies. Let me say a few words about us. We're AMFitzgerald. We're a MEMS product development firm. We have clientele around the world with over 125 clients served to date, ranging from startups to Fortune 100 companies. We're located in Burlingame, California, which is in Silicon Valley near San Francisco Airport, and we were founded in 2003. The photos along the bottom give you some sense of some of the work that we've done. All the way on the left in the gray photo, you can see a close-up of the micro pump. To the right of that in the blue photo is a functionalized needle tip. In the center with the concentric circles is an image of a micro-optic lens. To the right of that is a multi-colored image. This highlights some of our simulation capabilities. And finally, all the way to the right in the green is one of our RocketMEMS die. When I say that we're a MEMS production development company, what I mean is that we can offer the entire chain of MEMS product development, from all the way, ranging from the strategy, meaning either market strategy or intellectual property strategy, to the design of the device and the modeling of the device, to the process integration and the fabrication of your chips. We can prototype them and also offer low volume manufacture. When you're ready for higher volume manufacture, we can help you select the foundry and transfer that process to the foundry. And we can also assist you in packaging and testing your device. So that is our talk today on RocketMEMS, semi-custom pressure sensors. In summary, we gave a couple examples on how to increase system performance, how to decrease system cost, and how to improve system reliability, all with reduced development costs, times, and risk. If you'd like more information, you can visit our webpage at www.amfitzgerald.com/RocketMEMS. If you'd like to read some of the articles that I mentioned at the beginning of the webinar, you can find links at www.amfitzgerald.com/publications. And finally, if you have any questions after this talk or would like some of our die samples or one of our evaluation kits, please email us at rocketmems@amfitzgerald.com. Thank you very much for attending our webinar.